Let's tune a motor with Polaris Motion Control Systems. To begin, we're going to autophase the motor. Select autophase, select your axis, and then click Start. Now wait for the autophasing procedure to complete. With the procedure complete, you're ready to tune the motor. Go to the Tuning tab, select your axis. Now select the graphical SPU interface, and then click View Edit. I'm going to open the scope. This makes the tuning process much easier. So to begin, we're going to set all the parameters to 0. Looking at tap 6 and tap 12, we can monitor the input and output of the current loop. Select those on Motion Tools. Channel 1, I'll select tap 6, the input, and on channel 2 I'll select tap 12, the output. Select the channel 1 and channel 2 and click play, and we can monitor using the scope. We can change our vertical range by entering a maximum and minimum value. Here I'll look at a maximum and minimum of 0.2 amps. When you're first tuning an amplifier, you want to make sure you zero the current sensors. This needs to be done only the first time. Now I'll save those offsets. To tune the current loop, we're going to insert a signal into ACOM. To do that, I'm going to select an impulse motion type, input it on the ACOM channel. I'll start with an amplitude of 0.1 amps and a duration of 0.1 seconds. I'll change the feed-forward acceleration term to be a pass-through value of 1, and I'll start tuning with the current loop with a proportional term. Here I'm going to start with 0.05. Now I enable the motor and I inject the impulse signal. You can see it go by there. To make tuning procedure easier, we can turn the triggering menu on. So we'll continuously trigger on the command value. I'm going to trigger at a value of 0.1 and change my amplitude to be 0.2 amps. Also change the duration to be 0.2 seconds. Now when I inject the signal, you see it triggers. To see it more clearly, I'll increase the pre-trigger value, and I'll also change the minimum and maximum vertical range of the scope. So now we can easily see the effects of inputting the signal. We have the command in blue and the response in pink. And my motor's gone into falling air, so I'll disable that for the current loop tuning. So I need to turn up the proportional term, so I'll increase IKP. Let's look at the effects of that. Let's add some integral terms. We'll change the saturation value to 0.1. We'll set the integral branch of the current loop to be 0.01. Input the signal. You see the effects there. Lastly, I'm going to increase the proportional term of the current loop. This will help it rise quicker. And there we go, we have a pretty good response. I'm going to move on, or I'm going to add a filter here first. So to see the effects of that, I'm going to turn off the triggering, and I'll add a kilohertz low-pass filter. Click Apply and then Enable. Here you'll see the noise decrease substantially. And that finishes off the tuning of the current loop. Disable the motors. I'll go back to the motion type of motion, where I can give a command in velocity terms and give it a position target. So I'll send my motor between 10 and minus 10. Turn off the feed forward of the acceleration. Next I'll tune the velocity loop. So I'll set the feed forward velocity term, start with 0.01, and you want to balance that with the feedback velocity term, so I'll set it to 0.01, and I'll change the proportional velocity term with an initial value of 0.1. Now on the scope I want to monitor the command, which is going to be VCOM, and the feedback, which will be velocity. I'll trigger on the commanded velocity, add a value of 10. So now when I give a command, it's going to go into following error. So here I want to enable following error again. It's going into following error because it's not tuned well enough, so I need to increase the proportional velocity term before I get any response. So start with a small value, let's increase it. So now when I give a command, it's still not responding very well. So now I'm going to increase it by turning up the feed forward and feedback parameters. Again, these should be matched so that there's a balance. Now when I give a command, I have more of a signal and I get more of a response. So there you can see the command and the response. So we want to tune the velocity loop to get that as optimized as possible. So let's add some integral terms to the velocity loop. So now we have a pretty close match between the command and the response. So now we'll move on to the position loop. So I'll monitor the position command and the position feedback. Here it's known as encoder position float, or enc pause float in the scope. So we'll trigger now on PCOM at a value of 0, which is halfway between the motion target points. I'll turn the shuttle on so it continuously updates. So here I'll add a proportional term to begin with. I'll start with a small value. And here you'll notice the axis has gone into following error, so I'll re-enable the motor and then re-enable the shuttle as well. Now you'll start to see the effects of adding in the proportional term to the position. And one thing I haven't mentioned yet is that the tuning parameters don't update until you dereference the text box. So here you see I've updated the field, and it doesn't get updated until I click onto another text field. So now we add a derivative term to the position loop. Typically it's bigger than the proportional term. That should take care of some stability and improve the overshoot if there is any. So now we want to increase the proportional term some more to improve the response. You see the update happened partway through. And now when it triggers again, you see the full update. Now I'm ready to add some integral term. The integral term will improve steady state performance. So now when I zoom in, you'll see I have an acceleration error of about 500 nanometers and an imposition error of around 150 nanometers. And that concludes my demonstration of how to tune with the Polaris Motion Control System.